Unfortunately, the 5 axioms that I have presented to you don't have any way that I can grab all of these successors that I'm making, because I will repeat the successor operation until the cows come home. No one will stop me from successoring an ordinal. But what will allow me to grab all of the ordinals? How can I get all of them and put them inside of a set? Union isn't going to do it, because I need a set and I take the elements in it. So that's not going to help. Extensionality tells me when they're equal. This isn't going to make a set. The other axioms that I've showed as well. There are many other axioms that are in the axioms of set theory that I have not discussed, such as the power set axiom, many other axioms. But even these axioms are not strong enough to construct the set that we have in mind. So what do we have to do so that the natural numbers exist? We thought these were God-given objects, and now we're here trying to construct these God-given objects as laboring men and women that we are. So what do we need? The axiom of infinity. The class omega is a set. This is the axiom of infinity. So we find out that still, no matter how hard we try, it is still a belief that the natural numbers do exist. QED.
You just said that at the beginning.
Could I still have time. I can begin defining addition on these things. To show you how we have. To show that these aren't just numbers that satisfy Peano's axioms. We can do things with these numbers. So let's.
Turn the light on.
Oh yeah.
We need to clean the board, people.
Yeah.
We need to clean the board. What's that? The board is there.
In order to define addition, there are a lot of things that we need that I have not gone over already. And I haven't prepared this. But so I'm going to assume some knowledge, but I will explain what I mean. So if I have alpha ordinal and beta ordinal, I want to somehow have a guy that has more, that has as many elements as alpha plus beta has in mind. So let's consider 5 and 7. So what is 5? 0, 1, 2, 3, and 4. What is 7? 0, 1, 2, 3, 4, 5, and 6. So now, how do I construct a new set that is going to have 5 plus 7 elements in it? So the way we define this is we are going to construct 2 sets, and we're going to union them. So this is the set 5, this is the set 7. We will create the set 5 Cartesian product with the set containing 0. So think of this as attaching a color to every number, the color 0. Or I could do it in red. So we're giving a place to each of these numbers. We're assigning them a 0. We will likewise paint this number by Cartesian producting the set 7 with 1. So now there's a distinction between the 0 element here and the 0 element here. We have coded everybody here with this. So we define, first we have to take the union of these elements. So 5 cross, so we consider the set, so by axiom of pairing, this set exists, this set exists. So there exists a set with, so we have 5 cross 0 and 7 cross 1. So this is a set. By the union axiom, we can union it. So we have all of those elements in there. So 5 plus 7 is going to be defined as the ordinal that is in bijection. That is in bijection with this set. So what is a bijection? A bijection is a very natural thing that occurs to us. Bijections are how we count things. When I want to count how many computers I have here, I start by picking an ordinal. And I'm going to say, I'm going to map this 0 to that one. 1 to that computer. 2 to that computer. So then the collection of the computers in that row, except for that one, is in bijection with the ordinal 5. Because I mapped 0 to 1, 1 to that one, 2 to this. So a bijection has the property that every element is sent to a unique element. And I made sure that all of the elements were hit. So a bijection is a function that has two properties. It's a function f, which goes from a set x to a set y, such that for every y for every z and y, there exists xz such that f of xz equals z. So every element in here has been mapped to by someone in here. This is the onto property. We call this being onto. The other property we have is the one-to-one property, which says that if x is for every x1, x2 element in x, f of x1 is not equal to f of x2, implies that x1 is not equal to x2. So is that wrong? Well, I have inequality implies inequality. I'll take it. Take off the. So if two elements are mapped to the same element, then they had to be the same element. So we see that what I was constructing earlier between those computers and this ordinal is a bijection, because every element is sent to a unique computer, and every computer that I'm considering has been hit. So this is a bijection.
So you're saying bijections pair the elements?
Yes, the bijections pair the elements together. So what is 5 plus 7 going to be? It's going to be the ordinal that I can biject with this. So let's list out all of these elements. So we have 0, we have 0, comma 0, 1, comma 0, 2, comma 0, 3, comma 0, 4, comma 0. These are the elements of 5. We have 0, comma 1, 0, comma 2, 0, comma 3, 0, comma 4, 0, comma 5, and 0, comma 6. What am I? Yeah, what am I doing? I did this. No. We have 0, comma 1, 1, comma 1, 2, comma 1. So these are the elements of 7 and 1 in the second quarter. 0, comma 1, 3, comma 1, 4, comma 1, 5, comma 1, and 6, comma 1. So 5 plus 7 is going to be the distinct ordinal that has a bijection with this guy. What do you think that ordinal is going to be? Any guesses? 12. Okay, so let's look at the ordinal 12. The ordinal 12 contains 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I was going, you guys were getting answers. So, we can now construct this bijection. 0, 0 will map to 0. And like so. We will map all of the elements here in a one-to-one and onto fashion with the ordinal that we denote 12. This is how we define addition of these sets. So now we can start doing algebra, right? We have addition. we've turned our sets into beings now. Because we're starting to do math on them. I can also define multiplication on these sets. In a similar manner, with a bijection. The way that, because bijections are how we count them. So, we're going to be constructing bijections in order to do this. So now you can actually go home and tell your mom, you know how to show 1 plus 1 equals 2. It's not just something that your teacher says, 1 plus 1 equals 2. We now can show that this is true. So how do we define multiplication? So, given x, y ordinals, x multiplied by y is defined to be the ordinal in bijection with x Cartesian product with y, which is the set of all ordered pairs x comma y, where x is in x and y is in y. Now this is also very natural. Multiplication could be represented. So we have things on a grid. We have elements of x, and we have elements of y. The Cartesian product will have a whole row of these. So we take, so now we have 5 and 4, 7 and 8. So the set 5 Cartesian product with 4 has the elements 0, 0, 0.
2 and 3. 2 and 3.
3 by 3. 3 times 3. We'll prove that it's smaller. We have 0, comma 0, 0, comma 1, comma 0, 2, comma 0. Then we have 1, comma 0. 1, 0, comma 1, 1, comma 1, and 2, comma 1. Then we have 0, comma 2, 1, comma 2, and 2, comma 2. So, the unique ordinal that is in bijection with this set, we call it 9. And this is how we start defining multiplication. Okay, exactly. This is a good point. So exactly how we have it. Consider the Cartesian product. Consider 5 times 0. This is going to be the cardinal. We use these bars to denote cardinality, or the ordinal that it is in bijection with is the cardinality. This is going to be the cardinality of 5 crossed with the empty set. You can note the empty set. The 0 is the empty set. So the coordinate pairs are 1, comma. There's no one in here. So it's 1, 2, comma. There's no one in there. Oh, it's not. So it's just 1, 2, 0, 1, 2, 3, and 4. Oh no, that's bad.